Do you have any fun toys to share with us today? No fun toys?
Well, no, I still am
Oh,
enamored with this one. See,
well, that was from last month. Yeah, we
I
need
know, but
some new toys.
I'm still enamored with it. It's just so much fun,
All right.
for that.
So let's appeal to the audience. If anyone has any fun magnetic things they want them to
I I
play
need
with,
I need more cool magnetic toys.
I had some. I did not bring them.
Well, this morning we had interesting conversations with customers that have cool magnetic
Yeah.
toys. They aren't really toys; they're really super sophisticated things. But that was kind of fun.
Yes. And it's always interesting talking to someone outside the US to kind of looking at us going, what?
Yeah.
What's going on over there? We're just going to let a few more folks join in and get settled before we kick off here for a very lively topic, which with current state of affairs, we keep having to adjust the slides every 5 minutes, but hopefully they're current.
No, it's kind of interesting. It's a topic that we've been working on with other customers and clients. And I don't know, it was probably more than a month ago where we go, we should probably have a webinar about this.
Yes,
It just so happens that,
yes,
wow,
the timing.
what's good timing?
All right. Well, just out of respect for everyone who got here on time, I think we're going to go ahead and kick off. So, first of all, officially, everyone, welcome to our monthly webinar series. As many of you know, we're picking a specific topic around magnetics every month and taking a little bit of a deep dive onto this. We are pretty informal, as you may have already picked up. So, as you have questions or comments, my best to type them into chat and we'll try to answer them as we go along or we'll save them to the end if we need to. But this is pretty informal. We will be posting a recording of the webinar, so you don't have to be too crazy about taking too many notes because we will be posting that. So I do want to introduce today's speakers. First of all, I have Tim Costello with me, and he has had quite an illustrious career. He started his formative years at General Motors and launched the first EV1 electric car way back when. He did not star in the movie. So anyway, yeah, I don't know who played you, but he was then head of worldwide manufacturing for Applied Materials in the semiconductor world. He then founded and ran with me, actually, the Home Building Industries Technology Consortium for over a couple decades. And then his history with correlated magnetics, or as most of you know, polymagnets. He was one of the original investors and then stepped in more deeply just last year as CEO and heading up kind of the relaunch of the organization. And then also with us today is Mr. Steve Murray, who doesn't look this old, but he's been around for over 2 decades as an engineer, all mostly in the Huntsville, Alabama area. So defense and space and all of that with several different companies. And early on in his career, he was with Polymagnets. He left, couldn't resist coming back.
The attraction from polymagnets.
Attraction.
Steve, you should take your metal suit off. That you could have escaped.
I know. All right. We need to take this comedy show on the road, but really honored. And he's kind of, really the expert when it comes to polymagnets and the patterns and the capabilities and what we can do. So really excited to have both of them with us today. And I'm Melissa. I am the mags planer. So my job is to try to make polymagnets and magnets digestible and understandable by even those of us who are not engineers. So without further ado, I'm going to turn it over to Tim
Great.
to cover today's topic.
Thank you. Well, welcome everybody to North and South. That's what we're calling our Polymagnet webinar series. And every month we try to pick up a kind of a new topic or technique, and we'll talk about what our topic is at the end of this. Next month we have another really interesting topic for everybody. This month, though, we're talking about something super important for anybody that uses magnets, and that is designing for resilience. Potentially reducing the use of rare earth materials and really designing your supply chain so that you are not subject to all of the wild swings that we see today in either availability or pricing of rare earth materials. That's going to be the topic today. So I want to start first with just the problem statement. And, I think the very first thing we got to look at is just neodymium all by itself. Neodymium as a commodity is a fairly volatile commodity, subject to, pretty substantial increases in price. If you look at the period of from 2001 through 2002, over a period of just under 24 months, the price of neodymium had gone up 400%. Obviously, that means if you're using a lot of neodymium, your raw base material cost is going to go up, substantially. Even outside of that, though, there are shorter, periods of spiking costs from, 25% over very short periods of time. So it's, neodymium, it's a little bit of a challenge for somebody to go, look, I'm going to design a product. And I know what my magnetic cost is, and it's going to be fixed, and it's going to be fixed over time. With neodymium's history, at least over the last 4 years, it's very difficult to do that. Now, luckily today, we've got relatively low price compared to what it has been over the last few years, and we hope it stays stable. But it is a commodity, and it has been a fairly volatile commodity over time. The other problem that we have with neodymium is it is subject to political manipulation. And I've updated my chart. I hope it's completely updated.
Let me go watch the news
Yeah,
really quick
I
and
didn't
see.
go back years ago, but
Yeah.
the challenge is that governments abroad and domestic can put tariffs on things from other nations, and and it can cause wild swings. And because the vast majority of neodymium today all comes from China, there are companies all over the world trying to, build out a more robust supply chain in Vietnam, in Australia, in the United States, and different parts of Europe. None of those supply chains really hold the same economic or the same volume, at least today. So today we are kind of stuck with whatever the kind of political situation is with China. Now, on the other hand, with that is, China realizes that they have a pretty important strategic weapon, and that's rare earth exports. And if they don't like what the rest of the world is doing, whether it be the U.S. or Europe or other Asian countries, they can begin to throttle those rare earth exports. And just recently, they put some significant restrictions on rare earth materials, and those that did not include neodymium at the time, which was great. However, they are starting to clamp down. We received a series of force majeure letters from suppliers. I'm sure many of you have as well, from China, stating that there is a new Ministry of Commerce uh, uh, export requirement for all magnet shipments out of China now, that requires every single shipment to have its own kind of documentation. And this documentation can take quite a bit of time. So it's kind of just a way to administratively slow down some of the export of magnetic materials out of China, at least rare earth magnetic materials out of China. All of this may calm down, but for anybody that's trying to run a business, it does raise the issue of, is there anything that we can do to reduce the amount of rare earth materials that we use, or even potentially eliminate the use of rare earth materials, and yet still use magnets in our design? And that's really the problem statement, and what we're going to talk about into today's webinar. The one of the things that we do look at frequently is, before there was neodymium, there were ferrite magnets, and ferrite magnets are significantly less expensive than neodymium magnets. Ferrite magnets are made up of ferrite oxide and strontium carbonate. Um, they are, maybe about a tenth of the price. It depends on what you're trying to do exactly, but about a tenth of the price by volume is neodymium. The challenge is neodymium magnets are 10 times stronger than ferrite magnets. So, it's kind of a wash in the end. Uh, but as you're going to see, there are opportunities in design to substantially either reduce your exposure to rare earth materials, or dramatically reduce the cost of magnets in your design by integrating ferrite into some of your designs when you combine polymagnet. Now, ferrite does have some kind of nice characteristics. It is naturally more temperature and corrosion resistant than neodymium. So in some applications, this also helps dramatically, not having to move to more capable and specialized grades of neodymium. But I know what everybody says. We need strength. We need all the power that we can get. That's why we went to neodymium. Well, that's really where polymagnet can help. And I'm not going to give you a primer on all of Polymagnet, but I will just remind everybody in Polymagnet, what we do is we take signal processing, coding, and signal wave theory, and we apply it to magnetic fields. So the normal magnetic fields that you see that come out of magnets, we're able to shape and form those. And by being able to shape and form those, we just make magnets better. We make them stronger, we make them attach better, better for shear, better for torsion, and we do this by taking the natural properties that you see in this picture, where you have a square magnet where the magnetic forces are kind of concentrated on the edges and the fields wrap around the sides. Much of this magnetic energy, the flux that you see radiating from this magnet, is generally not used in design because it doesn't effectively interfere with the intersecting plane of work. What polymagnet can do is by encoding the magnet with a specific coded sequence of north and south poles on one rigid magnet, you can change the entire field structure, harnessing the power to make the magnets either stronger, meaning a greater attach or repel force. You can change the reach to focus on very thin metal attachments. You can shape the magnetic fields so that they work in electronics or in medical devices. You can combine functions so that a single magnet will have multiple functions and have all kinds of unique characteristics. And the list goes on and on. Like I said, I'm not going to give a primer on polymagnet, but when you take these capabilities now and you start thinking about how to design to reduce your reliance on rare earth materials or potentially be able to substitute completely away from rare earth materials, it comes into play. So, way back when, and these are very old charts, way back when Polymagnet started, they started to play around with how could we increase the force of magnets. And you can see the lower gray line is a traditional magnet, you see kind of on the far right. And then you see these design iterations as they began to play around with different configurations, they found that they could dramatically increase, in this case, the attachment force, the holding force of a magnet. You can imagine this allows you now to say, well, wait a minute, if I don't need more holding force, can I simply use less magnet? Yeah. Now you're starting to design for resilience. You're starting to reduce the amount of rare earth material that you need, or you can degrade the material and move to lower, less expensive grades, or completely eliminate the need for neodymium and rare earth materials altogether. And we'll show you some very specific examples in just a little bit. You can take this stuff to kind of an extreme, and you can get up to even up to almost 8 times the holding force of a magnet, depending on the kind of design and the thickness of the material and what you're trying to do. And you can kind of see how this works in this basic picture. And if you have one of our little sample kits, we always include these 3 magnets in that metal plate in the sample kits so that people can physically experience them. But the conventional magnet there on the left has all these fields. Many of the fields pass directly through the thin sheet of steel, not necessarily providing you much value. Many of them wrap around the magnet as well, kind of avoiding the steel. When you start to apply the polymagnet pattern, you're starting to bridge that field across the surface of the magnet, bringing it more in contact with that sheet of steel. And by doing that, you're increasing the effective force of the magnet. Obviously, you're not changing the chemistry of the magnet. You're not changing the grain structure of the magnet. You're not doing any of that. You're just utilizing the natural force that is already inherent within the magnet. You're simply focusing it on the plane of work so that you can get more out of the magnet. It can work in shear as well. Steve always reminds me that shear is really just the attachment force with the coefficient of friction. So, the more attachment force you have, the more shear that you have. Obviously, if you enhance then the coefficient of friction and you increase the attached force, you can really achieve some outstanding performance levels with respect to shear. And we have a lot of customers that use polymagnets in shear applications, and quite astonishing. I've actually seen video of children rock climbing on magnetic hooks. I mean, it just kind of blows your mind that magnets can have that much power in a shear situation. You can take shear to an extreme, and shear is also related to torque, of course. This is very specialized magnets that we created for torque that resist any kind of torsional movement. It's a pair of magnets, and we use these a lot in shows as demonstrators. You can see the very delicate, intricate patterns that are created, again, purposely built for a specific application. And you can go on and on. We've created all kinds of interesting, very high performance, 250 psi type, powerful magnets for lifting. But I think it's time to get on to now some case studies, very specifically of how do you actually go about design. And Steve, you've provided us with some data here, so we've got some charts, and I'm sure Steve will start to opine in, but we'll just start at the very beginning. Steve selected an N50 conventional 1-inch magnet. It is the blue dotted line you see on our chart. You can see that it on contact provides about 16 newtons of force. And then as you kind of move away from contact surface. And I think, Steve, this was all done with 10,000ths of an inch thick steel in this specific set of graphs. Obviously, there'd be a change for the kind of steel and the thickness of steel and all those kind of things, but this is 10,000ths that we're using in the situation. So from here, Steve, why don't you tell them what you did next, and I'll advance the slide. So your first recommendation or your first design was to create a polymagnet version of the same magnet.
Yeah, let me start with saying to do this, I wanted to use only what's on our catalog right now. None of these are custom designed. We didn't try and go as strong and best we could for any specific application. What I did is I took 10,000 steel because all of our data sheets on our website use either 10,000 steel or 31,000 steel. I'll also say I did the same kind of analysis for 31,000s. It followed roughly the same, and I'll get into where it differs a little bit. But every one of these are on our website until you get down to the two that are on the bottom, the two where I tried to match the conventional. So given that, let me start. All right. So the conventional is the dotted line. These all use N50. I'm not trying to change the magnet at all. So with N50, what we're able to do, if we put a polymagnet on here, we're able to get about 3.5 times the strength in a 1-inch magnet, same base magnet. All we did is change a conventional magnet into a polymagnet. That's just different magnetization. Okay. So 3.5 times the force. So you see, we're a lot stronger at contact. As we get out to distances between the steel and the magnet, there's going to be a time where we cross over. So in this graph you're showing with the polymagnet, the 1-inch, we cross over to where we're no longer stronger than the conventional, around about 3 millimeters. Okay. And each design that we give is going to have a different crossover range. So with the 1-inch, 3.5 times, as we move to a smaller magnet at 3/4 of an inch, same grade, still N50, just a little different pattern, then we're only 3 times the force. But we'd have 3 times the force in a smaller magnet already. Then we can continue on.
And you can imagine the amount of volume of material by going down from 1-inch to 3/4 of an inch is a very significant savings in the amount of material that you would use.
Yeah, and the way you'd look at this chart is saying, okay, well, I have a 1.4 millimeter gap or 1.3 millimeter gap in my application between the magnet and the metal. So what size of polymagnet would I need to get the same force that I would get with conventional? And that would be your 3/4 of an inch. However, if we're talking contact, it's even better. So on a 1/2-inch magnet, and I'll show you these differences. There's your difference in size between a 1-inch magnet and a 1/2-inch polymagnet. That has the same force all the way out to a 0.5 millimeter. If you're using it at contact, we're much higher force. If we now look at how we can save some more money besides just in the material, so we've already eliminated 76% of the material. So you're already a significantly cheaper magnet. However, what we can do then, instead of going to N50, we can reduce that to an N35 grade, which is your blue line. That gets you at contact, we have the same force as the 1-inch magnet. So not only did you reduce the magnetic material, you reduced the grade. So your cost is significantly lower. Okay. And then we're still in neodymium here.
Before we move out into
yeah,
neodymium,
let's do
I think the issue here, right, for most people is they have a standard, 1 inch neodymium magnet. They're buying it. They've got all kinds of price volatility, tariff issues, right? There may be constraints on supply, hard to get. What you're showing is that you can dramatically reduce, by 75% or so, the amount of material that you would use and get the same or more effective force than what they already have in a simple kind of attach type situation. Um, and this would be the same, of course, for sensors and all kinds of things, right? You're just looking for the amount of force at distance. So I think the first issue is, well, why are we wasting, 75% of our material when we don't really need that material in order to accomplish the task?
And we do have a typo here. That blue line at the bottom is
Yeah,
a half inch
it's a
in
half
real
inch,
life.
not 1 inch. It's the same as this. These two are
Yeah.
the same. Yeah. Yeah. Mhm. All right. So now let's move on to, if we wanted to really do something weird, how would we actually maybe even
Sure.
move this a step further and move to ferrite? So before we step to that, I want to make it clear our folks at DMEGC, great Chinese magnet company. They provide some of the world's best ferrite powders. Have shared with us, the different kinds of grades that they have, and the highest grade that they offer today is, what we would kind of consider kind of a 5.5 or something like that, right? Right around in that range. Whereas, of course, N35 is right around 35 and N57 is right around 55. So, neodymium is 6 to 10 times stronger, depending on the grade that you're looking at, than the best ferrites that are out there. But ferrites are about 90% less expensive than the neodymium at the same time. So, from that perspective, you kind of go, gosh, it's almost like a wash. Right? I'd need 10 times more ferrite in order to get the same, kind of forces. But Steve, when you start designing with them, it looks like you can really make some tremendous strides.
Again, and where I said I would get into the difference in the 31,000 steel, when we look at that half inch polymagnet against 10,000 steel, we can do it with an N35. If you are going to 31 thousandths, we need a little bit more of the field length in order to penetrate the 31,000 steel. So what you would then need to do, a N57 in a half inch polymagnet will then match the same grade on 31 thousandths, still match the same 1 inch conventional on 31 thousandths at contact. So that grade allows us to play a little bit and still keep a less magnetic material.
Yep.
Now moving to the ferrite, that's the brown line here. So we have to go a little bit larger. We have a lot less force, a lot less it's BH max in the ferrite. So what we have to do is then provide more material. So we go to a 1.4 inch, and we now have the same force as a conventional has at a 0.2 millimeter gap. So we are higher at contact with a 1.4 inch ferrite polymagnet.
I think what's interesting, even though you're using 40% more material by volume, the end cost of the magnet is in the kind of a 70 to 80% cost reduction range compared to the conventional 1 inch neodymium 50 magnet.
And a lot more available and a lot less tariff problems.
Yes, and we haven't seen anything with import restrictions, tariffs, any of these other issues with respect to ferrite, probably because ferrite's so widely distributed, all over the planet. There are lots of sources for it, etc. It seems to be able to kind of skate by some of that. Even in the magnetic materials force to measure letters that were sent out, I noticed they didn't mention ferrite magnets in that at all. So. So, Steve, we've actually been working with some customers recently. And I think we had a customer recently that had a fairly old neodymium application. What were they using originally? What was the grade of neodymium that they had spec'd in their design?
I don't know. It was bonded neodymium.
Yeah.
So it is lower force
Yep.
than sintered.
we were able, working with the ferrite supplier, to actually substitute directly the high grade ferrite for their neodymium, and they were able to achieve the forces that they needed for the product to work, and able to move from neodymium back to ferrite, which was kind of astonishing, especially in their condition because they were trying to work in a hydrogen environment, and that was the whole issue of why they were looking for ferrite to begin with. So they were able to migrate away from neodymium to ferrite, and quite successfully, and at the same time substantially reduce the cost and make their supply chain more resilient.
Right, and the magnet came out to be pennies.
Yes, the magnet was substantially less expensive. So, I'd like to open up to our audience just a little bit here first. Any questions about this? So, the basic theory here is when you add polymagnet patterns, you're dramatically increasing, the forces that you're seeing with the intersection plane of work. That allows you to, in many cases, designers go, yippee, I always wanted more force, and they don't shrink the magnets at all. But if you're really looking at supply chain resilience, cost reduction, mitigating rare earth materials, it does allow you to substantially reduce, as you can see, up to 75% the amount of the neodymium material that you would need to be using. And it offers the opportunity in some cases to even move beyond rare earth materials and moving back into ferrite magnets, and avoiding the rare earths altogether. So if the audience, if there's any questions out there about kind of how you do this or what kind of applications, if there's some limitations to this.
And feel free to type in chat, or you're welcome to take yourself off mute. So
yeah, either way.
Yeah, I have a question regarding that. Please consider that I'm totally new to this polymagnet word, and it's confusing me severely, even if I'm a technician. But it's completely disrupting to see this kind of stuff. I when I see this chart, I struggle to to understand some parts, meaning that you have this cross point around 3 millimeters, in where your magnet starts to be substantially lower in force compared to the standard magnet. I understood that you are able to play with this point, meaning that you can move it further or closer to the zero. But my main question, because I have an application in my mind for a project that we are now doing, is it possible to reverse this chart, meaning that you could have a lower attraction force in the starting point and a wider compared to the standard magnet, and a wider attracting force to the big distance?
We can provide less. That's not a problem. We can provide less. We are not going to be able to provide a longer reach, because remember, what we're doing is we're taking a magnet and it's normally got a long field length. We're now concentrating that however long we want it to be, but we can never go further than the physics allows the magnet to start. So we can't take a magnet that goes a couple inches away and then make it go 10 inches away. But we can certainly, by introducing repel, we can certainly lower it before that crossover point, wherever that crossover point may be.
So to your point, Steve, you can really inverse these lines. You can start at 0, right, and move up to, right, the kind of the dashed blue line way out at 5 millimeters, 10 millimeters, however far away you want it to be. Right.
Yes, there's that crossover point is going to depend on the pattern as well as the geometry and different factors. So I can't tell you where that crossover point is without knowing your magnet and your application. But yes, we can invert it to some point.
Thank you. Of course, our project is still it's still too young to speak about this matter now. But I'm sure that we will come back to you about our problems in this kind of application.
Great.
Well, mission accomplished.
That's right.
Let me explain that our catalog online, our stock offerings off the shelf are all in neodymium. But that doesn't limit us. Just because we have our catalog, we just use that as a way that you can order something off the shelf and try out with it. We can magnetize any permanent magnetic material. So it can be ferrite, it can be alnico, it can be samarium cobalt, neodymium, it doesn't matter.
And according to you, Steve, it can be steel as well.
I didn't say that. That's a soft magnetic material. We need hard magnetic materials.
Oh, it's just
We can use steel to make a stronger magnet. That
Yes.
doesn't mean we magnetize it. That means what we can do is we can take away magnetic material and we can add steel
Yes.
by doing that. So let's say we have a 3 millimeter magnet. We can probably get the same. This is off the top of my head. Don't hold me to these numbers. We can probably get the same kind of force if we took away half of that. Let's say we have a 1.5 millimeter magnet and a 1.5 millimeter steel. We can probably get you the same kind of force. That allows you to then reduce the magnetic material again and use some cheap other substance to get back up to the same force.
So it's really another design parameter that we have here, right? So we have the polymagnet pattern, and then we have the polymagnet pattern in conjunction with backing steel, right? That can again substantially increase the forces and offer the opportunity to reduce the volume of material or the grade of material, or to substitute completely and move to ferrite. Now, we haven't included that because there are a variety of different ways to use that backing material to get higher strength. The number of degrees of freedom of design here would start to get a little bit crazy. I think it's super instructive for the industry right now, though, to understand that we really should be thinking about optimizing the use of neodymium material.
right. But
Ready to move on?
I'll keep
All
an
right,
eye on
very good.
questions. Yep.
All right. The other thing that's important to recognize is that polymagnet, the manufacturing process, uh, is very simple. It does not require huge industrial power applications. It's not a dirty process. The machines are not huge. So the machines can quickly be relocated and set up. I mean, you literally could drive a machine or ship a machine by air to another site and have it hooked up within 24 hours. This allows manufacturers, if tariffs exist or other restrictions to trade exist, to simply move your operations and optimize your operations by moving your operations to a country that is not being impacted by those barriers. Again, because polymagnet completely transforms the function of the magnet, then the same way you take a magnet and you put it in a motor, and then the motor is not subject to the tariffs of the magnet supplying nation. It would allow you to be able to work around many of these tariff issues. So that's a whole nother component of how you can kind of make your supply chain more resilient if you are using polymagnet as a magnetization process.
Yeah, that's a really good point because, just depending on what country you do your final assembly or where you manufacture, and then these tariffs, it just gives you a lot of flexibility.
It's a volatile world. The politics change minute by minute, but polymagnet it allows you to have the versatility to quickly respond and be able to have a very robust supply chain where you can find yourself where you're not having to be subject to, most of these kind of draconian tariffs. So in the end, what polymagnet can do for you is we can reduce the amount of magnetic material that you use by up to 80%. You can design in some cases with lower grades of neodymium, which may be more plentiful or less expensive. You can even substitute alternative materials such as ferrite for neodymium in certain applications if you have the volume and the real estate, and along with that, achieve substantial cost savings. And then you can quickly and effortlessly move your production to territories and countries to avoid supply constraints and tariff. So, all said, a polymagnet is really kind of your solution for a resilient supply chain. And we'd welcome to have further discussions with any company to talk about how you could optimize your supply chain and make it resilient and reduce your costs and volatility that you see out in the market. You can always reach out to us. You can connect with Polymagnet all the time by emailing us at connect@polymagnet.com. You can follow us on LinkedIn. And if these kinds of discussions are useful to us, We have a webinar every single month. North and South is a normal feature on our calendar. The next one will be May 8th. We're going to focus on new frontiers in magnetic processing technologies. We're going to be talking to a partner company that does 3D injection molding of magnets, which allows you to create interesting topographies to solve all kinds of magnetic problems. And they'll be with us on the 8th of May, and we hope that you are as well.
Perfect. All right. Well, hopefully this was interesting to everyone. When I was just watching the questions, I did see a question come in, and it says, "Do you guys do collaborations or partnerships for R&D?"
We do a lot of that.
We love doing that. We love doing that. Yes, we do. Because we're constantly curious, and every time we have a conversation, there's kind of new things that start to emerge. So definitely, let's follow up after this webinar. And I would say if anybody has interest, you can reach out to us. We love having just kind of quick 30-minute Zoom chats, and that kind of helps us, quickly assess, can we help? Can polymagnets help in any way? So always happy to do that. So we have another question coming in. What is the name of the company that does the 3D injection molded magnets?
Man, we're gonna go out there and they're gonna learn everything before we even have our webinar.
They can help. They can be a guest speaker if they're going to do that.
Yeah, it's a great company. It's a German company called MIMS, and they have a really interesting technology. So that can solve all kinds of interesting problems. They can even they can direct the grain structure of the injection molded magnet in process so that the grain structures are not uniform throughout the entire part. Many times you don't want the grain structure all to be oriented in the same direction, but you don't want it to be random. You may want the grain structure in one portion of the magnet to be oriented in one orientation, and another orientation in another portion of the magnet. They've achieved all of this over a long period of time. It's a very worthy technology to discuss. You combine that then with the ability to magnetize these different zones of grain structure with the polymagnet process, and there's some neat opportunities there. So that's what we're going to talk about in May. But if anybody needs to rush out and contact them right away, we'd be more than happy to make the introduction to you. They're a wonderful technology company based in Germany.
Yeah, we met them when we were over in Amsterdam.
Yes, we did.
Actually. So interesting. All right. Well, I don't see any other questions coming in, but I did put in my email in the chat, or you can reach us via connect@polymagnet.com. Happy to connect up with you and help with your solutions.
Thank you, everybody, for attending, and hope to see you next month.